In this lecture, we will introduce a concept which is very important for especially the engineers who are working in power substations and dealing with electrode resistance or grounding resistance of various electrodes. So, we will try to see how to utilize whatever we have learned up till now to find the resistance of a ground electrode. So, let us see how to do that. Now, in one of the previous lectures, when we derived the boundary conditions for homogeneous media for the current density, we found that del cross J by sigma is equal to 0. And since we are considering a homogeneous media, so del cross J is equal to 0, and it implies J can also be written as a gradient of some potential function, which is a scalar function. So accordingly, we told that there will be a corresponding Laplace equation. So the method of images which is applicable for electrostatics should also be applicable for the condition having a homogeneous media with steady currents. So let us assume that ground is homogeneous media. Of course, practically it may not be the case. So we are assuming that this is ground with sigma epsilon as a material constant, and there is a ground electrode which is buried in this soil. Now, since sigma is equal to 0 of the air, so we know that there cannot be a current density in the air. Now we have also seen that J1n is equal to J2n, that is the normal component is continuous. So since there is no normal component in the medium 1, that is air, so it implies there will not be any normal component near the interface. So all the flux lines of current density should move like this. Now you can easily imagine, if it had been a symmetrical case, these flux lines would have been like this. So these kind of field lines can be drawn if we can assume that this medium is now surrounding everywhere and this boundary line is not here now. Everywhere it is sigma epsilon. So this kind of flux lines can be drawn if there is an equal source. If it is plus I, then it will also be plus I, similar to plus q charge combination. So for this case, the flux line will be like this. So you see that we can use method of images for solving our problem with homogeneous conducting media. So for a case, let us say that there is a hemispherical electrode which is buried in the soil, and this electrode is having a radius of a. Now we need to find the resistance of this hemispherical electrode which is buried in the ground, and we are assuming that it is just buried. Okay, so what we will do, we will make remove this interface and assume everywhere there is this soil, and we will take an image. So its image will be like this. So if this is current I, then it will be current I. So total current will be I plus I, and by symmetry, the total current will be like uniformly radiating out from this sphere. So the density will be 4 pi a square, or current density will be 2I by 4 pi a square, or I over 2 pi a square, and in radial direction. So in this way the current density can be found out. Of course, if I try to find at a distance r from the center, then this a will change to r, because everywhere due to symmetry these are going to expand radially. These lines are going to expand radially, so the current density at any point can be given as I over 2 pi r square in the radial direction. Now we need to find the value of the resistance of this grounding electrode. So the grounding electrode resistance is defined as the resistance between the electrode and the uh, uh, true ground, which is supposed to be available at infinity. That is having a total true potential of zero value. So we know J is equal to sigma E. So it implies E will be J over sigma equal to I by 2 pi sigma r square AR. So if this is the field, then the potential of the electrode will be V is equal to minus E dot dl from infinity to the electrode surface, or it will be E dot dl, changing the limits now, taking minus sign in the limits, this one. So putting the value, now dl is simply dr in the radial direction. So it will come out to be I by 2 pi sigma r square dr, where r is going to vary from a to infinity. So v is going to be equal to I by 2 pi sigma a. So this will be the potential of the electrode. So resistance will be R is equal to V by I is equal to 1 by 2 pi sigma A. So in this way we have found the resistance of a hemispherical ground electrode. So of course in practical scenario the electrode is not a hemispherical one, it is a vertical rod which is buried in the soil, but we have got some sense or idea how to go ahead with the calculations. Now let us try to calculate step potential. So let us say this electrode is carrying a fault current I, and a person is standing nearby, and the distance between the feet of the person is d. So because of this current spreading in the soil, there will be a potential difference between these 2 points which are at a distance d. So the potential difference will be delta v is equal to I by 2 pi sigma distance of this point and this point. Let us say first point is at r and second point is at r plus D. So delta V will be equal to I D 2 pi sigma R, although I was using capital R everywhere, so let us follow that same convention, capital R plus D. Now let us try to take some suitable values for an idea how much voltage this can be. I am assuming that person is having a foot spacing of 1 meter. This is a standard value which I have taken, and let us say the person is not having full 1 meter spacing between his legs. Let us say it is 0.75 meter. It is little more practical for our country. So let us say this D is equal to 0.75 meter, and this person is about 1 meter away from the center of the electrode. That is, this R is equal to 1 meter, and let us say the current is 1000 ampere, which is normal value for a simple substation. This fault current can be very easily achievable. And let us say the soil is having a conductivity of 0.01 Siemens per meter, or rho is equal to 1 by sigma is equal to 100 ohm meter. Again, 100 ohm meter is a typical value which is found in normal soil. So this is not again a very artificial case. So putting all these values, delta V will come out to be 6800 volts. So this value is very large. So between the legs of this person, a potential difference of around 7000 volt, and that is this 6820 volt is existing. And if this person is not wearing any shoes, and his feet are, let us say, little moist or wet, then the contact resistance will be very low, and this whole potential difference will appear across his legs, and he will get a huge shock. So you see, whenever a ground electrode is carrying a fault current, then we should be very careful while going near it. We should not go near it, because there will be a hazard of static potential if the design of the substation grounding is not proper. Now this 100 ohm meter is not a very fancy value, it is very practical value. So this is a very practical case. Of course, we have assumed that the electrode is just on the surface and it is hemispherical. Now, in this way, we have shown that method of image is applicable for current problems, especially for a homogeneous media case, and we have shown how to calculate the ground resistance of an electrode. Now, for you, I will leave a numerical example or numerical question for practice at home. What if there are two electrodes, two hemispherical electrodes carrying current I and minus I? Then what will be the resistance of this system? I will tell you the value. It will be 1 by pi sigma A, where A is the radius of this electrode. So for our case, we found it was 1 by 2 pi sigma A. For this case, it is twice. So I hope you will be able to solve this numerical and get this value. It is very easy, and nothing much is required to be done here. Only superposition is required. So I hope you will be able to solve it yourself. And if you find that this lecture is helpful to you, then please share and subscribe our YouTube channel, and also join our Telegram group, whose link is given in the description of this video. Thank you.